Hey everybody, welcome back to Mr. Aparicio's geometry course. Today I got a quick little lesson on reasoning and counterexamples for you. Let's get into it. When we solve problems in geometry, we use something called inductive reasoning to help us solve these problems. And inductive reasoning is just the observation of patterns in specific cases. So in any given problem that we have in geometry, we may observe a pattern that might be similar to something that we learned previously. And we've learned to recognize that pattern in any given problem. Then we're able to recall the processes that we learned in order to solve that problem. That's inductive reasoning. I have a few mathematical statements here for us to get a better idea of what inductive reasoning is. Go ahead and take a look at these four little sets of addition and multiplication here. And then start thinking and noticing the patterns that you see that they have in common. And whatever you think of, whatever you see, I want you to write off to the side. If you're my student, you're filling that in to the right here, describing the pattern. One thing you might notice is that we have addition in every step of the way. We have multiplication in every statement here. We are also adding three numbers together for each line here. All right, we're also multiplying a number by 3 for each line. You may notice that all these numbers are consecutive, 3, 4, 5. We're not skipping an integer in each set here. You might also notice the number we're multiplying by 3 happens to be the middle number for each of these that we're adding. And then hopefully you see that both the left side of our equal signs and right side of our equal signs, that those functions yield the result in the middle. 3 plus 4 plus 5 is 12. 4 times 3 is also 12. This addition gives us 24, that multiplication also gives us 24, and so on. So we can have these individual recognitions of patterns in all of these statements that we can write off to the side here. But then we can come to a conjecture. After we've recognized all these patterns, we can put them all together in one statement that we believe to be true for the statements that are given to us. Okay? Notice I said we believe to be. We don't know for sure that it's true until we get to something a little later on. So a conjecture is an unproven statement that is based on your inductive reasoning. I apologize for my handwriting as we go here. Again, a conjecture is an unproven statement that is based on inductive reasoning. So all those thoughts that we thought of when we looked at these can be put together here in one statement, which says the sum of any 3 consecutive integers. So we have consecutive 3, 4, 5, 7, 8, 9. The sum of them, we're adding them all up to get those values in the middle of our equal signs here. The sum of any 3 consecutive integers is 3 times the second number. Okay, so here we have the sum of 3 consecutive integers, and that is equal to 3 times the second number. 4 was the second number, 8 was the second number, 11 was the second number, and so on. So that's one statement that attempts to explain the patterns that we've observed in these statements. And the process that we go through as students here in geometry is like this. We do inductive reasoning, we recognize patterns, then we come up with some sort of conjecture to say, like, hey, I think this is true for everything that I'm observing. Then we can test to see if our conjecture is actually true or not, and if it applies to the problem that we are trying to solve. And what we'll often recognize is that the conjectures that we make sometimes are not true. They do not apply to the problems that we are trying to solve. And so the way that we know that something is not true is if we have a counterexample for that thing. So a counterexample is just a specific case that proves a conjecture is false, that it is not true, right? For an example, we have a conditional statement here that is a conjecture. Conjectures can often look like conditional statements. It says, if you live in Florida, then you live in Orange City. This is not a true statement because there are plenty of other cities that you can live in and still be living in Florida. So the counterexample would just be providing an example that makes this false. For example, you could live in Orlando instead of Orange City. You could live in Miami or Tampa or Jacksonville or Tallahassee or any other city, right? So the counterexample is just one thing that proves a statement is false. I really like this conjecture because a lot of people, if they don't think about it too much, will think that this is true even though it's not. If two angles are supplementary, then one of the angles must be obtuse. Hopefully you recall supplementary angles have to add up to 180 degrees. And so a lot of people read this statement and they think, yeah, that's true, because I need like 80 and 100 to get all the way up to 180. Right, but what we may forget is that you can have two right angles that are supplementary to each other, because 90 plus 90 equals 180. Those are supplementary, and neither of those is obtuse. They're right angles, not obtuse angles. So that is a counterexample there. 90 plus 90 equals 180. That proves that this statement is not true. And guys, that's it for this lesson, right? Just really quick thing about reasoning. Remember, that is your observation of patterns in given problems, and then counterexamples that can help you determine if what you're thinking is true or not. If you have something that proves a statement is false, that is a counterexample. Again, that's it for today. Quick little lesson. We'll see you in the next one, guys. Bye.